This video is an extension on a matplotlib tips and tricks video I posted earlier, and targets a thing that caused a lot of frustration for me and wasted a lot of time in one of my animation projects. That is how to animate things that move using Python and matplotlib. Anyways, there are many ways to do it, and what you want to use depends a lot on what animation you have in mind. Here are some things to consider. This does not include methods that are available in TakeInter and PyQt because they're GUI libraries. And this is about doing things where we only want to write some animation to file without touching anything GUI related. These are only the things I tried, and there may be better ways to do it. First, I'll set up an experiment where the end result looks like this. And it takes a little while to go through, so if you're only interested in the implementation of the methods, the timestamps are in the description, so just skip there. The animation is going to be a cloud in the sky. I'm not going to draw the cloud myself. If one wants to draw some picture programmatically, for example using a patch in matplotlib, there's some possible speed ups when rendering, but I'm not going to do that. Instead, I find some open source pic and then print screen it with the same size I want it to appear and move it to drawing program of choice, crop whatever I want from this picture to other pictures with desired dimensions, and then manually draw the border of the cloud or whatever else, and using some color. In this case I will use black color as background because the white should be distinguished from something else. I also save the background without the cloud. I start a project in PyCharm, and now I'll go through how to get the window up using matplotlib. So I got the folder with the pictures in there, get the necessary imports, there are some different ways how to set up a figure. I like that one. The axis, so that's like the scales on the X and Y, we don't need that here. Okay, got our window. I will now write some code to load the pictures into matplotlib. I will create a utils module where I will put the loading function. So here I use imread, and there's several options of how to load pictures. And some of them have some nice pre-processing functions, but I like imread because then we get a NumPy array out of it. I put it into this dictionary called pics, and I have the background and the cloud. I will also have separation in the cloud between like outer and inner. So now the axis I just created above is going to be populated with imshows of these pics I just loaded. So I get the ax as an argument, and now I'm gonna also put pointers to these ax objects in a dictionary or a list. Some of them have advantages and disadvantages. I'll go through that later. Since we don't need the background to actually change with the animation, I will only just show it directly to the axis without creating any pointer to it in this imax. But the cloud ax is going to be modified through the animation. So then I have a pointer to it. And Z orders, as you can see, are arranged in the right way, and I also do something with alpha here, and that's usually good because it's nice to see through when you're debugging. Okay, so I put this into Emacs, and then I can PLT show it. I also need to change the extent of the map, because otherwise it will just think that it should just plot the latest picture that was showed, I think. So yeah, now everything shows. So you can see the cloud had black behind it in the picture, and now we'll replace that with zero transparency, or maximum transparency, sorry. And therefore I create this add alpha layer module. So by the way, this could have been done in a drawing program, but I just prefer to do it in code. And the picture is in RGBA, but we only need to work with the red layer here because it's such an easy picture to separate, because it's just white. You could also see that I had this inner and outer cloud. So the inner cloud is smaller than the outer, but that's just for decoration. So the inner cloud will be kind of like less transparent than the outer one, just to make it look a bit better. And then I create some arrays where I threshold on this red value, so for the inner and outer cloud. And then the cloud alpha layer, so the fourth one, becomes the addition of them. This could have been done in several different ways, and even nicer would have been to use a distribution to create the alpha, but whatever. Here are the results. I think it will look better when I actually show the picture. Yeah, so here you can see it. And now I will add the animation loop skeleton. And I use func animation here. There are some other options like artist animation, but I like func animation. And it has this compulsory animate function where I is the frame, and it returns this list or dict of drawables, so the ones I added in Axe. I want to animate it for some number of frames. I set it to 100 here, and I don't want it to repeat. Now I will write the extent log, which is the data needed for this matplotlib one-liner to just set the extent at each frame in the animation. And I'll do that through numpy array. So I'll have this this 4-column array that just gives the left, right, bottom and top borders of the image at each frame. That's going to be the extent log. So the shape of this is going to be number of frames as rows, and then 4 columns, left, right, bottom and top borders. And it's going to be both shifting and growth of this cloud. So the shifting is the movement from left to right, and I call this position vector. So that one also has a numpy arrays here with number of frames as rows and 2 columns. And then the velocity of the cloud is going to be 0.8 pixels in X per frame and minus 0.1 pixels in Y. So it's going to grow, or I mean move from left to right and bottom to top. I have some starting coordinates, and then I fill this position vector with the correct values. And then I just set it up so that it also runs. And then I can see these actual values here as it moves. Just good to debug. And then the second part of this is scaling. So it's also going to grow from left to right and bottom to top. And the size of the cloud is going to start at 0.5, so it's going to be half as large as when it ends. It's going to stop at full size. And so the first column, which is the left border, is going to be the same as the position vector first column. So that one is fixed, and the bottom border is also already fixed. But then the width and the height are going to change. They're going to grow through time. And Yeah, could have been done inside the previous loop, but whatever. So the width is going to be width times scale vector, and same with height. And then I just put these values into the correct location in the extent log. So plus width and minus height. And now I will implement the setExtent one-liner using this just created data. First I get the pointer to the cloud axe in this Emacs data structure, and then I set the extent using extent log at frame I. And you can see here that it both moves and grows. I'll now add some blitting to the code, which is really nice to speed up the animation when it's running live, like I've done so far. So then blit equals true, interval equals 1, that means this is going to run as fast as possible, and then this init func is needed, and it's just going to return this Emacs. And you can see that it runs much faster, and then if I set the interval to slower, then it's going to run slower. You can see the cloud still has the black thing, and that's because I forgot to change the folder. But you could see that there's two clouds plotted now, and that's this weird blitting thing, which makes the cloud which is plotted on the first frame not go away. So my solution there is a hack, and to first set the alpha of the cloud to 0 and then set it to 1 at frame 1. Now I'm going to try to write the animation to file. So if write variable is not true, then plt show it as usual. Otherwise, save it to file. It's MP4, and then using some writer. For writer, I'll set it to an FFmpeg writer built into matplotlib. Then one needs frames per second. I will set it to 20. And then this metadata, which I don't know what it means, and bitrate, which affects the quality of the animation. I will make the cloud move a little bit slower here, and then make it save. When saving, it's nice to have this if mod condition, because saving might take a while, so it's good to have it printed out, like which iteration it's at. I noticed that the cloud aspect ratio is a bit wrong, and that's because I set the wrong variable here. It should be height instead of width. I'll just fix that. I think it's a little bit too fast still, so here it's slowed down a bit more and then written again. And you can see the result on the left here. And as you can see, it's a little bit choppy, and I don't really know where this quality loss happens. Okay, time for the next method. So I comment out this nice one-liner, and now it's time for Affine 2D using the built-in matplotlib transform. By the way, spoiler alert, this is a failed attempt. I'm trying to get the smooth motion with this method, but I failed with that. But here is the commands at least to do it. So there's this transformation matrix M, and I want to apply scaling to it. Just the cloud grows, and since I've already computed the scaling vector, I can just feed that there. So the scale in X and Y is provided here. And then I apply a translation as well, so that's the movement of the cloud using Shift X and Shift Y, which I've also have pre-computed. The order of the transforms does matter, and I try some different ones there, but I've actually failed to get the cloud to move exactly the same as in the setExtent function. It's definitely possible to sort out, but the intention of trying this method was to actually provide a smooth motion, and that failed in the end. But here's the commands to run it. The cloud appeared upside down, so I tried some different settings here to fix it, and in the end I hack it just by flipping it upside down using this numpy function. And then save it to file. And you can see the result in the middle, and you can see that the choppiness has not been removed. The next method is warpAffine in OpenCV, and for that implementation I will pre-compute some triangles. I think I could have used triangles in the matplotlib affine 2D as well, but I didn't. So I'll put this function compute triangles in model, and it will take the same kind of parameters as extent log, the compute movement. But this one is slightly less intuitive, like you have to think about triangles at each frame. That is still pretty straightforward. I will begin by creating a triangle with 3 coordinate pairs, and I'll put that in a list of triangles, and this is just going to be a normal Python list. I could have used a numpy array, but for debugging I think it's slightly easier to look at triangles in a list because they're kind of nested. So the first point is going to be bottom left, and the second point is going to be middle top, and the third point is going to be bottom right. That's what these P0, P1 and P2 mean. And then I store that as a numpy array and put that in the triangles list. And then at each iteration I am updating the position of this triangle. So this is both translation and scaling, because I've pre-computed all of this in the extent log that gives the extent of the cloud at each frame. So I can just query the values from there to update the 3 coordinate pairs of the triangle at each frame. Yeah, and since the extent log, it only contains floating point values that come from linear spaces, it shouldn't be any data quality loss here. Yeah, and then I keep appending this to the triangles list, and then it's returned. This iteration should actually start at 1. And then moving back to the animation loop, I'll begin by commenting out set alpha, because I will do that later in a different function. And then I extract 2 relevant triangles, which is the base triangle T0, which is from the top of the list, and then the triangle at the current frame. And then there is this Emacs thing. So now I use the list there, but when you write it to file, it takes forever, or at least using this method. I have no idea why, so I have to change it to dict here for some really weird reason. But the dict doesn't work with blitting, so if you want to run it live, then it's slow down. But yeah, you have to. Writing to file is usually more important than showing it live. Then the cloud is removed from the Emacs, and then the transformation matrix is created based on the two triangles, and then the picture is warped. And you can see that there that I put 1280 720 as the extent of the warp, which is a bit unnecessary, and it takes a bunch of compute to actually, if it's too large. So it's good to minimize that to the largest extent to the transform or whatever. It takes a little bit of extra code that I don't go through here, but it's good to minimize the extent of the warp. And you'll see if it's too small if you animate it. And then I can imshow it with the Z order and alpha there, whatever I want. Comment out the blitting and then view it. And the contrast at the border of the cloud is a bit too much here, so I changed the transparency thresholds to 0.1 and 0.9 between the inner and outer clouds here. And then I write it to file. By the way, I also fixed this this contrast issue for the outer border for all the scenarios, so set extent and affine 2D in matplotlib. And you can see the OpenCV result on the right here, and that it's moving much smoother than the other ones. I will now do some profiling, starting with the setExtent method. So I'll get the list for Emacs back, comment out things I don't need, and then just use time.time to get a basic idea of how fast things are. And that comma needs to be removed when it's list. So about 0.0002 seconds for live showing, and then much faster for writing. And set transform in matplotlib is even faster. It's about twice as fast in both showing live and writing to file. So it would be really nice if one could just get that smooth motion in there. I couldn't figure out how to do it. And for CV2, warpAffine, that's by far the slowest one. I think it's about 100 times slower than the other two methods. Let's get the code there to run with it. One could try to pre-compute getAffine transform and warpAffine and store them in memory, but that would be storing a picture at each frame, so it would be very expensive memory-wise. Also, in my code I removed the cloud from the axe and then reinserted at each frame, which is kind of stupid, so there should be a better way to do it. But warpAffine is the line that eats most CPU time there. Some things I haven't mentioned in this video, but that can also be done, is to write some assertions to test that the maximum minimums in extent log or triangles, that they don't go outside the boundaries of the background picture. It's usually good for debugging. And there's also more fine transforms one can do, like flipping and shearing, and then one can change various light settings of the pictures, like brightness and saturation with the frames to make it look better.